Hello everyone, this is Chandrakant Mishra. Today we are going to discuss the transient analysis, that is last portion of the transient analysis. So we'll start with an example. So in this example, find the response V0t for the input xt as shown below. The circuit is this, that is your resistors and another is a capacitors. So input is applied here as a xt and they have asked the V0t. So input is 1 for in between 0 to 1, right? So and input is 0 otherwise. So you can easily say that it is a pulse from 0 to 1 actually exists. The amplitude is 1. This is actually of xt, and you know the decomposition. So I can write x of t as u of t minus u of t minus 1. So taking the Laplace transform of both the side, right? Initially we are assuming that there is no initial charge across the capacitors. So this is 1 and this is 1 upon s. So I assume that I have applied ut, right? So ut, so this side I will have 1 upon s, clear? So I assume that my input is ut only, right? Then we will, because it is LTI, so we will response of the response of the system for every input will be added together. I applied the input this, so its Laplace transform will be 1 upon s. So my circuit converted into a Laplace transformable circuit or Laplace transformed circuit. This is 1 upon s, this is 1, then it is 1 upon s, and this is my V0s. So V0s upon V0s is equal to, this is simple potential division, that is 1 upon s upon 1 plus 1 upon s into 1 upon s, right? So s plus 1 into s, right? So make a partial fraction. So a upon s plus b upon s plus 1. So by using the Heaviside's relations or Heaviside's expansions, you can find the a and v. So it is a easy one. So just multiply s both the side, and then put the s equal to 0. So that will give you a equal to 1. Similarly, b, multiply s plus 1 both the side and put s equal to minus 1. So minus b will be minus 1, s plus 1, right? So I got the V0t taking the inverse Laplace transform. This is 1 minus e to the power minus 1 ut, right? Because this is the unilateral Laplace transform. So we'll consider the inverse Laplace transform of 1 upon s is the ut, and minus 1 upon s plus 1 is the e to the power minus t ut. And the beauty of the LTI system tells that if input xt produce an output yt, the input xt minus t naught will produce an output yt minus t naught, being a time invariant, and also it is LTI. So next section is, so what will be the output for input ut minus 1? So ut minus 1, so your output will be, for input ut minus 1, your output will be 1 minus e to the power minus, wherever t like this you replace t minus 1 u of t minus 1, That means this portion is starting at same replica of the original portion, this portion, but it starts at 1, t equal to 1, not before 1 or not after 1, it just start at 1. So when you assemble together, because our input is u of t minus u of t minus 1, also system is linear. As linear, you know, the homogeneity will be satisfied. Whatever will be multiplied, your output will be multiplied by that constant. So finally for this input, your v0t will be the 1 minus e to the power minus t ut minus 1 minus e to the power t minus 1 u of t minus 1, right? So I want to draw this. What will be the form of? Very easy, right? See here, this term, you know, when t is 0, it is 0 starting from 0 here, right? And it will go like this till it achieve 1. This is your 1. But what happens? It is 0, but at 1 exactly we got a replica here, right? Like this. If we allow this, it will reach minus 1, right? So this portion is your critical one. So ultimately the response will be the this. Then when it is increasing, it start decreasing. So ultimately it will be like this. So this will be the response. That is your V02. When we apply a square pulse, or you can say rectangular pulse, the form will be a approximated triangular. We'll move to the next. So let us see this question. So in the circuit shown below, the switch S is open for a long time and is closed at t equal to 0. The current IT for t greater or equal to 0 plus is. This is a great question. Okay, so it says that switch is open for a long period. Okay, let's see. When the switch is open for a long period and switch is closed at t equal to 0, we need to calculate before switching, that is all the quantities for 0 minus. So I will draw the circuit for t 0 minus, that is just before switching. Inductor will act as a short and switch here because it is open just before switching, right? And this is your I and T. Okay, this is your 10 ohm, this is 1.5 ampere, and this is your 10 ohm. Okay, now find out. This is your IL. So IL 0 minus is equal to this much current. So you can see here 10 ohm resistors, here 10 ohm resistors. So the current will be equally divided. So 1.5 ampere upon 2, that is 0.75 ampere. Okay, because only one energy storing element. Now we'll look at the conditions when switch is closed. When the switch is closed, the circuit becomes like this. Inductor will act as a current source because IL 0 plus is 0.75 ampere. So at t equal to 0 plus, this is your t equal to 0 plus 1.5 ampere. It doesn't make any sense, still we have to write 10 ohm. this is your 10 ohm, this is your 10 ohm, right? This is your 0.75 ampere, and this is your the current, because what are the question? IT here, IT. Right? So now I'll find the it is a very simple condition. So whatever the current is coming, the 0.75 is going here, and then we left with the 1.5, it is going 0.75, we left with the how much? 0.75 ampere. So 0.75, because this is the current in going through the both the equal resistors, so I0 plus will be the, because equally divided same the current 0.75 upon 2, that is 0.3 then 375 ampere. Okay, now we'll take the conditions for t equal to infinity. When t infinity, the current source as usual would act as a short, 10 ohm, 10 ohm, here also 10 ohm, then current source, that is inductors, because at t0 plus it was a current source, but it is a inductor, so it will act as short. So you can again see that this current is 1.5 will be divided equally, because 10 ohm, 10 ohm, 10 ohm. So your I infinity, so we found I0 plus is 0.375 ampere. Then I infinity is equal to equal division 1.5 by 2, that is 0.5 ampere. Okay, now next move is that how to find the time constant from this circuit. You see, when the circuit is closed, okay, what will be the time constant? The rule is the energy source reduced to 0. When I reduce the energy source to 0, it's a ideal current source, so the current source will act as a open. So what the inductor see? Inductor sees that when we look from this side, this is closed, 10 ohm parallel plus 10, so 15 ohm. So R equivalent is equal to 15 ohm, and then L is your 15 millihenry. So your time constant will be, the tau will be L upon R eq, L upon R eq, that is 15 upon 15, that is 1 millisecond. So general relation, because it's a step function, constant current, so we know that I of t is equal to I of infinity minus I of infinity minus I of 0 plus e raised to the power minus t upon tau. So your I infinity, how much you got? That is 0.5 minus I infinity 0.5 minus I0 plus, that is 0.375, then e to the power minus t upon 10 to the power minus, or you can say 1 millisecond. So ultimately 0.5, how much it is? 0.125, right? 125 e to the power minus 10 to the power qt, and ultimately ut. This is the response at 10 ohm, or you can say after switch is closed, the current flowing through the switch. Very simple. Whenever there is a single time constant, doing this circuit this way would save lot of time. Okay. So we'll move to the next question. That it has been appeared in the GATE 2021. The circuit in the figure contains a current source driving a load having an inductors and resistor in series with a shunt capacitors across the load. The ammeter is assumed to have zero resistance. The switch is closed at equal to 0. So in a nutshell, this is the circuit. Okay, you have capacitors, inductors and resistors and an ammeter and 1 ampere current source. Initially when the switch is open, okay, initially switch is open, so it is clearly indicated in the circuit. The capacitor is discharged and the ammeter reads 0 amperes. That means all the are in their you can say the dead state or 0 state. After the switch is closed, the ammeter reading keeps fluctuating for some time till it settles to a final steady value. The maximum ammeter reading that one will observe after the switch is closed. Okay. First of all, ammeter is connected here. That means the current, when the switch is closed, the current will flow through this and also through this. We need to find this current. Okay. So final current, obviously capacitor will be fully charged. The ammeter in the steady state after the switch is closed, the current will current read by the ammeter is 1 ampere. So when the switch is closed, so capacitors and inductors and resistors forms a, along with the current source, forms a circuits. That means a second order circuits, because you know that there are two storage element of the different kind, so it will be second order circuit. And it asking the what will be the maximum ammeter reading. That means a peak value will be there, because second order systems, and in that case in a second order systems the peak value only occurs when your damping is under damped. That means resistor value, that is zeta, is less than 1, between 0 and 1 and less than 1, then only it will have a peak value. Otherwise, if under damped or over damped case, critical damped case, you cannot cross above final value, that is 1 ampere in this case. So there are two ways you can do it. Okay, if you identify the circuit properly, right? So as I told you how to identify circuit, so reduce the current source to 0 and the circuit becomes a series connection between the capacitors, inductor and resistors. So the characteristic equation for these circuits will be the x square plus r by l, but for series circuit r by l upon s plus 1 upon lc equal to 0, because we know that is the, from the characteristic equation we can find the zeta, from the zeta we can find the peak value. Okay, so for parallel RLC, suppose you reduce the current source to 0 and you see that the circuit becomes a parallel RLC. So that will be for parallel RLC, it will be s square plus 1 upon RCS plus 1 upon LC equal to 0. So for the current case you have, this is the characteristic equations. So s square, r is your 5 into 10 to the power 3, L is equal to 10 to the power minus 2, S plus 1 upon LC, L is equal to 10 to the power minus 2 and C is equal to 10 to the power minus 10 equal to 0. So s square plus 5 into 10 to the power 5 s plus 10 to the power 12 equal to 0. So omega n equal to 10 to the power 12 root over, which is 10 to the power 6. 2 zeta omega n is equal to 5 into 10 to the power 5. So zeta is equal to 5 into 10 to the power 5 upon 2 into omega n, that is 10 to the power 6, that is 10 to the power 5 and 10 to the power 5 cancel 1, 10, that is 5 upon 20, which is 1 upon 4 or 0.25. This is your zeta value we come. Now once you found the zeta, so you can find out the peak value. This is the peak value of the, that is peak value is equal to 1 plus e to the power minus zeta upon 1 minus zeta square root over into pi. So 1 plus e to the power minus 1 upon 4 upon that is 16 minus 1 upon 4 root over into pi. So finally 1 plus e to the power minus pi upon root over 15. So you will get the 1 plus 0.444 with the help of calculator. So peak value will be the 1.444. That will be read by the ammeters, that is the maximum value read by the ammeter before settling to the 1 ampere. So this is the way. Another suppose you miss this case actually, so obviously you will, because some in the exam hall obviously you will may slip from the mind that you cannot I want to say yes, this is after switch is closed the ammeter reading keeps fluctuating, sometimes the maximum ammeter. See, the if you slip this point maximum ammeter reading, and this maximum ammeter reading is connected to the underdamped system. Suppose you missed, so obviously the second process is the, you just go through the converting after the switch is closed, so all the values are initial, the circuit will simply becomes like this. So this is a 1 ampere, so 1 ampere is the 1 upon s. Then a capacitor switch has been closed, so capacitor 1 upon cs, so 10 to the power minus 1 upon 10 to the power minus 10s, so 10 to the power 10s. Then you have ls 10 to the power minus 2s, 10 to the power minus 2s. Then resistors 5 into 10 to the power q. Okay, so ammeter is connected here, that means this current, so I is equal to current division, so 10 to the power 10 upon s upon 10 to the power 10 upon s plus 10 to the power minus 2s plus 5 into 10 to the power q and into 1 upon s, because the current division we have done. So you have 10 to the power 10 upon 10 to the power minus 2s square plus 5 into 10 to the power 3s plus 10 to the power 10. It is not in the standard form of the characteristic equation, so take 10 to the power minus 2 common, so in the numerators you have 10 to the power 12, so s square plus 5 into 10 to the power 5s plus 10 to the power 12. In this step, if you could identify that the question is from the underdamped case, it has been asked the maximum value, then into 1 upon s there, into 1 upon s, that we need to calculate the maximum peak value, then plus add 1, so that we can get the maximum reading of the ammeter, then you can easily get it. Otherwise what happens, you try to find, so obviously you need to think smartly in the gate exam, because if you calculate the IT So what is the process? Actually somebody is going to do the in this way. So first he or she will find the it, then differentiate it upon dt equal to 0, then find the t. So all these steps will take lot of times, because already we did this in the control system transient analysis of the control system. So from with this process we have found mp, that is percentage overshoot, right? mp percentage overshoot is the e to the power minus zeta upon zeta upon 1 minus zeta square into pi. We have found out that is the percentage of overshoot. So if you don't call into 100, that is percentage of overshoot. So with this properties, or with this concept in the mind, if you have worked out the problems and you can correlate with the things, then you know that this is the end of your problem. Just find the zeta as we have done in previously, and you will get the result as usual, 1.444. okay, nobody does this way, conventional way, because you already know the standard relations for this. Okay, hope you guys have learned many things about the transient analysis. Please, the secret for the your success, or I can say the secret for the high score or high rank in the GATE lies with your practice. That is clear and crispy understanding of the concepts and continuous practicing of the questions papers. You can start with the that is a previous year questions, at least 10 years. So start browsing through all the previous year questions. Start doing on your own before going through the keys or solutions. Unless you do that is, you try once, try twice, try thrice, definitely at the third attempt you will do the questions. So the wrong way is the first students go through the solutions, then they try the question. That is absolutely a disastrous way to practice for the GATE questions. Unless you develop the problem solving ability, that comes from the practice on your own. Stretch yourself to the maximum level after the learning concept. Once you are thorough in the learning concept, definitely you can crack almost all questions of the GATE, that is all the previous year GATE questions. And make sure that you alert sometimes for revising the concept what you have learned already, right? That you learn something previously, and over the time, over the months, over the days, you tends to forget those concepts. That has to be taken care of, right? And one more thing is, just try to study I can say that is line by line of textbook or your notes. Try to understand, try to analyze the things. It is not only required for the GATE to click like this novel example. This is a very clever questions and very conceptual questions. So once you think analytically instead of just memorizing the formula or concept. You can analyze yourself, give some time. For example, in a given day you give 30 minutes just before going to the bed. Just analyze yourself in the mind, what you have learned, how they are interconnected. You know that picture makes our memory sharper when you correlate between the relation. Suppose you have a let's say transient analysis. Here L, here C, here R, like this. L will be LS. All the make the if it is initial voltage, so LS, then LS, then minus I0 upon I0 L for voltage transform. If it is a capacitor, it is 1 upon CS plus B00 upon S. Just try to do this analysis, and then definitely it will be very much helpful in the last hour of the exam, during the last hour of the exam, during the revision, and you have enough time to revise and practice from the test series, previous year questions, all the stuffs, all the questions which you see on the different platform. So put your best effort. Okay, there is no shortcut to the success in a single word. You have to study, you have to put the smart efforts, then you have to develop the aptitude with analysis and synthesis, you can say. So keep yourself in the toes, and keep on going, solving the questions of the different question sets, and definitely you will develop an aptitude for the problem solving. Next we will start the two-port networks, and if you have any doubt, you can comment in the in my YouTube channel, or you can send me the message in my Telegram group. Okay, see you in the next class. Till then, take care. Bye bye. Happy learning.